5 students haven't filled up the form. I see that all of the students attend the class today. Okay, today class is fully online. Okay, no face-to-face class. Okay, due to some reason. Okay, one of the reason is my personal reason. Okay, I cannot make it to campus, and another reason is most of the students they cannot come to campus as well. Okay, some some students they come to campus last few weeks. Okay, but this week they cannot come. Okay, so I just decided to make it fully online. Okay, today's lecture I will finish the chapter 6, okay, about the dynamic logic circuit, okay, and also I need to brief you on the assignment. Okay, I have upload the assignment to you last 2 weeks. Suppose I need to brief you last week, but I forget. Okay, today I have to brief you, and then with the deadline of submissions. Okay, I will inform you of the deadline of submissions for lab report. Okay, not lab report, is assignment report. Okay, after I finish my lecture, if I forget, please remind me again. I scared I forget again. Okay, now I will start my lecture. Okay, this topic, I still have a few slides to cover. Okay, I didn't manage cover it last week. Okay, today I hope I can cover in this 1 hour lecture. Okay, and then before I continue with the slide that I stopped last week, okay, I want to recap what has been covered last week. Okay, for this dynamic logic circuit, okay, I have covered about the pass transistor circuit, okay, and also another circuit, we call it a voltage bootstrapping. Okay, okay, what is the difference between the dynamic logic circuit and static logic circuit? Okay, dynamic logic circuit, okay, there is a clock. Okay, there is input to the circuit. Okay, this is how we differentiate the circuit, okay, between static and dynamic. Okay, so you see here, this is the pass transistor circuit with the clock. Okay, when there is a clock and there is a load capacitance or output capacitance, okay, means that this circuit is a dynamic logic circuit. Okay, and then the transistor used is also a CMOS transistor. Okay, in this circuit only NMOS is used. Okay, NMOS. Okay, there is a few more of the circuit here has introduced to you. Okay, about pass transistor circuit. Okay, so these are the circuit, we also call it as pass transistor circuit, all consist of NMOS. Okay, and then they are connected together. Okay, and then the output, as you see here, this is the output. Okay, output is VDD minus VT. Okay, means there is a drop at the output. Okay, due to the circuit here constructed. Okay, and then some of the uh, elements. Okay, this circuit, it seems that the output has dropped. Okay, the VDD minus VT, this is the threshold voltage. The Vout is not equals to VDD when Vout is high. Okay, it is affected by the drop of the threshold voltage. Okay, what does it mean? This one you will have to study back. Okay, Okay, so this is another one, pass transistor circuit, okay, with different structure, but also used NMOS. Okay, and the output here also it is influenced by the drop of the threshold voltage. Okay, so this is one of the problem. Okay, we consider it as a problem. Okay, the technique that can use to overcome this problem is the voltage bootstrapping. Okay, what is voltage bootstrapping? Okay, it is a dynamic circuit technique that can use to overcome the threshold voltage drop in digital circuit. Okay, this I have explained to you before. Okay, how this is applied, and then how the circuit, okay, can use to reduce or overcome the threshold voltage drops. Okay, the use of the circuit examples is given here. Okay, this is circuit examples. Okay, and then okay, these circuit examples is with the voltage, the threshold voltage drop. Okay, the V out is not VDD. Okay, is VDD minus the threshold voltage. Okay, to overcome it, okay, so this will be the circuit. Okay, this is the circuit we call it as dynamic bootstrapping circuit. Okay, there is additional capacitance or capacitors that is added at the input of this transistor M2. Okay, and also another transistor M3 is added. Okay, this circuit with the additionals of the transistor and capacitor, okay, they can be used to overcome the threshold voltage. Means that in this case, the V out will be equals to VDD. It's not with VD. It's not VDD minus the threshold voltage. Okay, so you can revise back. Okay, I have uploaded the lecture notes to you. Okay, in Google Classroom, you can go and download and have a look on the content and do your revision later. Okay, so today I will continue with another type of the dynamic CMOS logic. Okay, I will introduce the domino logic circuit and also NORA logic circuit. Okay, um, both of them is not difficult to understand. I will cover the fundamental one. Okay, so no worry. Okay, so this is the dynamic CMOS circuit. Okay, before I cover on the domino logic circuits and the NORA logic circuit. Okay, this is one of the dynamic logic circuit, okay, that I will introduce to you first. Okay, so a dynamic CMOS circuit technique which allowed to significantly reduce the numbers of transistors used to implement any logic circuit is introduced. Okay, in a dynamic CMOS circuit, okay, it can also use to implement complex Boolean function. Okay, previously the circuit that I show you is only a very simple circuit, okay, and structure, okay, with only NMOS, okay. But now this dynamic CMOS circuit, the next few slide that I'm going to cover is to implement the complex Boolean function, okay. The circuit operation is based on first pre-charging the output node capacitance and subsequently evaluating the output level according to the applied input. Both of these operations are scheduled by a single clock signal which drive one NMOS and one PMOS transistor in each dynamic stage. A dynamic CMOS logic gate which implements the following function is shown in figure 9.26. Okay, a dynamic CMOS circuit is operated with a clock. Okay, so if we refer to this figure 9.26, the clock is defined by this phi. Okay, this is a clock. Okay, a single clock. Okay, and then when there is a clock, then the process and the operations of this circuit, okay, there will be two. Okay, one is a pre-charging. Okay, pre-charging process and discharging process. Okay, the pre-charging process here means there is a charging up occur across the capacitance. Okay, you may wonder that where is the capacitance? Here mentions that output node capacitance. So where is the capacitance? So at the output here, there is a capacitance. Okay, and then when the clock, okay, is low, okay, this PMOS will turn on, so there will be current flow. Okay, so this capacitance will charge up. So we call this process as the pre-charging process. Okay, and then here the V out will be VDD. Okay, and then if the clock transit from low to high 1, so means that PMOS on, PMOS is off, and NMOS is on. So the output will change, okay, and it will change depending on the input voltage of the transistor here. Okay, this is 5 transistor. Okay, we consider this dynamic CMOS logic circuit that is implement with complex Boolean function. Okay, this is actually the pull down network. Okay, pull down network. Okay, when I say pull down network later, you will know. Okay, when I explain the domino logic circuit, okay, you will know why this is a pull down network. Okay, so here already show the diagram, the processes and operations of this circuit. Okay, when the clock change from 1 to 0 or 0 to 1. Okay, so this is the clock signal. Okay, low and high and low and high. And then of course, when there is a change in the clock, then the output voltage also will change. Okay, so this is the voltage level at the output at different process. Okay, now I will explain further on the operations of the circuit here. Okay, when the clock signal is low and high. Okay, at the pre-charge phase. Okay, at the pre-charge phase means that the clock signal is low. Okay, so you see here, this is low clock signal. Okay, the PMOS is on, V out is high. Okay, and the NMOS is off. Okay, so this one is easy to understand. Okay, the parasitic output capacitance of the circuit Cout is charged up through the conducting PMOS transistor to a logic high level of V out equals to VDD. The input voltages are also applied during this phase, but they have no influence yet upon the output level since ME. ME means the NMOS is turned off. Okay, so at pre-charge phase, only PMOS is turned on. Okay, this is PMOS. Only PMOS is turned on. Okay, so the output will be influenced by the on state of the PMOS. Okay, and the NMOS here. Okay, this is NMOS. Okay, they will not influence the output. Okay, this is off, the NMOS is off. Okay, so the V out will not be low. Okay, it will maintain high. And then here, the input voltage, just now I mentioned. Okay, the input voltage this is the input voltage for A1, A2, A3, B1, and B2. Okay, so the input voltages are also applied during this phase but have no influence. Okay, so when the clock is low, so we see this diagram, this is the clock when it is low, Ck equals to 0. So the V out here is high, this is VDD. Okay, this phase we call as pre-charge phase. Okay, another operation is when the clock signals is high. Okay, we call it as evaluations phase. Okay, so in this case, you see that the PMOS here is turned off, okay, and NMOS is turned on. Okay, when NMOS turn on, means that the V out will reduce. Okay, it will reduce or maintain high. Okay, so I refer back to the statements here. Okay, the pre-charge transistor NP, this is PMOS turn off and the NMOS turn on. The output node's voltage may now remain at the logic high level or drop to a logic low, depending on the input voltage level. Okay, if the input signal create a conducting path between the output node and the ground, C out will discharge towards VOL equals to 0. This is 0 volt. Okay. The final discharge output level depends on the time span of the evaluations phase. Otherwise, V out remain at VDD. Okay. So I think some of you maybe you can understand what is meant by the statements here. Okay. When this NMOS is turned on, okay, the output will reduce or maintain high. Okay, in what conditions that the V out will maintain high? Okay, we have to see the input voltage to the transistor here. Okay, the input voltage of A1, A2, A3, B1, and B2. Okay, if none of these NMOS is turned on, okay, means that the V out will be high. Okay, if the input voltage, maybe this transistor, all the input voltage is high and then all NMOS are turned on and then they are conducting path to the ground. Okay, so the V out here will be 0. Okay, will be low and it is equals to 0. Okay, this is how we should understand. Okay, for practical multi-stage applications, however, the dynamic CMOS gate present a significant problem. Okay, just now I missed this one, the diagram. Okay, the high clock signal when this is high, okay, the clock is high, we call it as evaluation phase, right? Okay, so according to the diagram here, okay, when the clock signal is high at the evaluation phase, then the V out here, it will reduce to 0 or it will still maintain high. Okay, depends on the input voltage to the transistor. Okay, so this is the meanings of the diagram here. So now I goes to the next one. Okay, high performance dynamic CMOS circuit. Okay, next circuit to discuss are modifications of the basic dynamic CMOS logic gate structure. They are designed to take full advantage of the benefits of dynamic operation. Its ultimate goal is to achieve reliable, high-speed, compact circuit using the least complicated clocking scheme possible. Okay, the circuit examples are the domino CMOS logic and LoRa. Okay, LoRa logic circuit. Okay, so these two circuits are modification based on the basic dynamic CMOS logic circuit. Okay, the basic one is the one that I showed you in the previous. Okay, now I will introduce to you about domino CMOS logic. Figure 9.28 shows the generalized circuit diagram of a domino CMOS logic gate. Okay, this is what we call it as a domino CMOS logic gate. Okay, what is the difference of this domino CMOS logic gate with the basic dynamic logic circuit? Okay, this one is a dynamic logic circuit which I have shown you in the previous slide. Okay, and then this is the domino CMOS logic circuit. Okay, you can compare these two. Okay, the structure is almost the same, just that a CMOS inverter is added in domino logic circuit. Okay, this is a CMOS inverter. You see the structure and then the transistor used here. Okay, PMOS and NMOS. Okay, this is at the output. Okay, to the CMOS inverter, and this part is actually similar to this one. Okay. Okay, this part is similar. Okay, with PMOS. Okay, here also PMOS. Okay, and then NMOS, and this is also NMOS. And this part, it is called as NMOS logic. Okay, this part, this is represented as NMOS logic block. Okay, so they are of the same circuit structure. Okay, just that in domino CMOS logic gate, at the output, it is connected to the CMOS inverter. Okay, so this is the difference. Okay, so now I will mention about the operations of this domino logic circuit. Okay, since there is also a clock to the PMOS and NMOS, so the operation is quite similar to the first one, okay, that I mentioned to you without the CMOS inverter. Okay, so we also will consider the clock when it is low and high. Okay, for this domino logic circuit. Okay, this domino logic circuit is also one of the dynamic logic circuit, except that this is modified. Okay, it is modified based on the basic one. Okay, so there are two operations. One is when the clock is low. Okay, and this is we call it as a pre-charge phase. The output node of the dynamic CMOS stage is pre-charged to a very high logic level, and the output of the CMOS inverter becomes low. Okay, so you see here, okay, already stated to you. Okay, when the PMOS is on, okay, it is on because the clock is low. Okay, the Vout is high. Okay, when the Vout is high, then this CMOS inverter will invert the high input, okay, to a low output. That's why here is low. Okay, and then another operation is when the clock is high. Okay, this is what we call it as evaluations phase. Okay, there are two possibilities. The output node of the dynamic CMOS stage is either discharged to a low level through the NMOS circuitry, or it remain high. Okay, consequently, the inverter output voltage can also make at most one transitions during the evaluations phase from 0 to 1. Okay, this one is also the same conditions. Okay, I already mentioned just now. Okay, the output can be high or low depending on the input voltage to the NMOS transistor. Regardless of the input voltages applied to the dynamic CMOS stage, it is not possible for the buffer output to make a 1 to 0 transitions during the evaluation phase. Okay, so the change of the output at the output of the inverter in a CMOS inverter and also output of this uh, dynamic logic circuit can only make once. Okay, the transitions can only make once. Okay, not multiple. Okay, and also again have to depends on what is the input voltage. Okay, to the NMOS in this NMOS logic block. Okay, when there is a dynamic logic gate is with the CMOS inverter, we call it they are in cascaded okay form. Okay, the CMOS inverter is in cascading with the dynamic logic gate. Okay, and also okay, this is another structure we call it as a cascaded domino CMOS logic gate. Okay, cascaded means that there are two dynamic logic gates. They are connected, cascaded. Okay, they are connected in cascade. Okay, and you see here. Okay, this is the dynamic logic gate. The first one. This is the second one, and then in between there is a CMOS inverter. Okay, this CMOS inverter connect to the output of this logic gate. Okay, and then the output of the CMOS inverter is connected to the input to this logic gate. Okay, and then this dynamic logic gate, there is also a CMOS inverter connected at the output. Okay, means there are two domino CMOS logic gate. Okay. Okay, so the operation is also similar. Okay, determined by the clock. Okay, there are two phase with the pre-charge phase and also evaluation phase. Okay, so here you can also read yourself. Domino or CMOS logic gates allow a significant reductions in the numbers of transistors required to realize any complex Boolean function. Okay, why domino is says to have significant reductions in the numbers of transistors? Okay, there are two diagrams here. Okay, these two diagrams you can compare. Okay, the numbers of transistors used. Okay, this is the static logic gates. Okay, we call it static logic gates. You have learned this before. Okay, and then this is the domino logic gate. Okay, this is examples for you to see the difference. Okay, between the static logic gates and domino logic gates. Okay, the Boolean functions is given for this diagram. This diagram is implement with 8 input Boolean function. Okay, so this is the Boolean functions using standard CMOS and domino CMOS. Okay, and then there is a reductions of circuit complexity. Okay, the reductions of complexity is true by eliminating the pull-up network. Okay, this is PMOS, this is pull-out network, this is NMOS, this is pull-down network. Okay, when you see these domino logic gates, okay, only the pull-down network is maintained. Okay, in this circuit. Okay, and then the pull-up network already removed. Okay, and the numbers of the transistor used, okay, reduced. Okay, and then other circuit, you see there is some changes in the structures. Okay, in these domino logic gates, okay, there is a PMOS, only one PMOS, okay, and then another NMOS. Okay, remember that these two NMOS, these two transistors, okay, PMOS and NMOS, they are compulsory in domino logic gates. Okay, these two transistors is driven by this clock. Okay, so the operations of this circuit will be based on these two transistors. Okay, that is driven by the clock, and then of course the output will be changed. Okay, output at this logic gates will also change, and also at this output will be changed. Okay. Conventional static CMOS logic gates can be used together with domino CMOS gate in a cascaded configuration. Okay, the limitation is that the numbers of inverting static logic stage in cascade must be even so that the input of the next domino CMOS stage experience only 0 to 1 transition during the evaluation. Okay, so you see here, this is a figure 9.31. This is cascaded domino logic gates. Okay, these cascaded domino logic gates, okay, they can cascade with multiple domino logic gate, but the number must be even. Okay, number must be even. This is the limitations. Okay, we cannot simply cascade any numbers of the domino logic gates. We must make sure that the number chosen must be in even. Okay, the reason already stated here. Okay, to ensure that the input of the next domino CMOS stage experience only 0 to 1 transition during the evaluations phase. In domino CMOS logic, all logic operations are performed by the NMOS transistors acting as pull-down network, while the roles of PMOS transistors is limited to pre-charge the dynamic nodes. Okay, if you understand what I described about the operations of the dynamic logic gates, then you will understand this statement. Okay, so PMOS transistor is limiting to pre-charge the dynamic nodes. Okay, means that when PMOS is turned on, okay, then it will charge up the capacitance, okay, at the output. Okay, in this circuit, even though the capacitor is not shown to you, but you must assume that there is a capacitor, okay, at the output of this circuit. Okay, this is um, to this is to let you know that um, with the presence of the capacitance, then there will be a charging process. Okay, they will be charged up and discharged. Okay, so there is a capacitor. Remember that there is a capacitor. Okay, this you see the diagram here. Okay, this is a domino CMOS logic. Okay, and the NMOS logic is identified. Okay, for these 4 transistor with input A, B, C, D. Okay, so we can label this as the NMOS logic. Okay, okay, this is the stick diagram. Okay, for this domino CMOS logic. Okay, this stick diagram I think not difficult to understand. Okay, it is it is with the polysilicon layer. Okay, and then the metal layer here. Okay, the connections all are based on this circuit. Okay, this is NORA CMOS logic. Okay, just now I mentioned it's LoRa, right? Not NORA. Okay, now I confused already. Okay, I need to double check. As I remember, it is NORA, not LoRa. Okay, so this one here, okay, there's a spelling mistake, so it will be NORA. Okay, so next is another dynamic CMOS logic. Okay, we call it as NORA CMOS logic. Okay, the difference between NORA and domino is NORA use PMOS and NMOS. Okay, just now the domino also use PMOS and NMOS. Okay, but the PMOS used in domino is as a pre-charge transistor. Okay, but in this NORA, okay, later you will see the structure. It is not only used as a pre-charge transistor. Okay, the logic block also can be consist of the PMOS transistor. Okay, this NORA CMOS logic is an alternative and a complement to an NMOS-based domino CMOS logic. Figure 9.37 is a dynamic logic circuit with alternating NMOS and PMOS logic stage. Okay, this is figure 9.37 with NORA CMOS logic consisting of alternating NMOS and PMOS stages. Okay, you see all these are cascaded. Okay, there are three domino logic circuit and they are cascaded. When they form together, then we call them as a NORA CMOS logic. Okay, so this one, since each of these circuit here, they are in cascade, this is a domino. So still there is a PMOS prephase, a pre-charge transistor. Okay, PMOS is a pre-charge transistor, and then NMOS, okay, this is discharge transistors. Okay, already labeled here. Okay, so you see here, this is two transistor and also there is a logic block. Okay, the logic blocks here, okay, can be the NMOS and also PMOS. Okay, so for this NMOS logic, okay, this is the one we saw uh, in the previous slide. Okay, we call it as domino, but this one, okay, this one we um, does not call it as domino. Okay, the structure is domino, but then here the logic block is a PMOS. Okay, it is a PMOS. Okay, and then with this all the logic blocks, okay, they are connected to each other through the CMOS inverter. We call them NORA. Okay, the operation is also similar. Okay, it's driven by the clock signal. Okay, this is clock signal. Okay, the clock signal is by separate clock signal to the respective PMOS. The pre-charge and evaluation timings of NMOS logic stage is accomplished by the clock signal. And then while the PMOS logic stages are controlled by the inverted clock signal. Okay, so this one, the clock here with a bar means this is a inverted clock signal. Okay, means that if the clock signal, this is 0, okay, then this one, the clock signals will be equals to 1. Okay, for this NORA CMOS logic, the operations is given here, okay, with description. When the clock signal is blocked, the output nodes of NMOS logic blocks are pre-charged to VDD through the PMOS pre-charge transistor, whereas the output nodes of the PMOS logic blocks are pre-charged to 0 through the NMOS discharge transistor driven by this inverted clock signal. Okay, when the clock signals makes a low to high transition, the inverted clock signal will make a high to low transitions simultaneously. Okay, so the statements given here, okay, you can refer to this diagram again, figure 9.37. Okay, this diagram already stated to you, okay, when there is a clock 0, okay, then here the output will pre-charge to VDD. Okay, and then when the clock to the PMOS for this circuit is 1, okay, the PMOS, this PMOS will turn on. Sorry, it is turned off, okay, not turned on. Okay, this is off, the PMOS is off. Okay, and then this NMOS will be on. So here you see there is a conducting path, and then the output here, this output is 0. This is what is meant by this one. Okay, and then this circuit operates similar with this one. Okay, since the clock, okay, is of the same law clock signal. Okay, that is the operations of NORA CMOS logic. Okay, there is another circuit examples for NORA CMOS logic in figure 9.38. Okay, so this is a figure 9.38. It's also a NORA CMOS logic circuit. Okay, we can know it is a NORA CMOS logic circuit because you see all these logic circuit are connected in cascade. Okay, and then with PMOS and NMOS, okay, in each of the logic gates. And then you see each of the logic gates here, okay, they are with NMOS, okay. For this one, this is a NMOS logic block, okay. This is a PMOS logic block, and this is a NMOS logic block, okay. So we can know that this structure is similar to this one, okay. Okay, so there are advantages uh, of LoRa CMOS logic, okay, compared to Domino. Domino has its own advantages. NORA also has its own advantages. Okay, in NORA CMOS logic, okay, these are the advantages. A static CMOS inverter is not required at the output of every dynamic logic stage. Direct coupling of logic block is feasible by alternating NMOS and PMOS logic blocks. It is compatible with Domino CMOS logic. Output of NORA NMOS logic blocks can be inverted. Okay, and then apply to the input of a Domino CMOS block, which is also driven by the clock signal. It allows a pipeline system architecture. Okay, this is the another figure, figure 9.39, okay, to show you a pipeline architecture system for a NORA logic circuit. Okay, so there is an illustration here, okay, for the circuit given in figure 3.3, 9.39A, B, and C. Okay, a circuit in figure 9.39A is called as fine section. Okay, fine sections, this is actually indicated as a clock. Okay, it's driven by a clock. Okay, when all stage of this circuit perform pre-charge discharge operations when the clock signal is low, and all stage of circuit evaluate output level when the clock is high. Okay, you see here the figure, 9.39a, the clock to the this circuit with NMOS logic block. Okay, this is the fine section. Fine, we call it as a fine sections. Okay, for this whole architecture. Okay, why? Because the input that is driven is by this clock signal. Okay, and then followed by the inverted clock signal. Okay, and then for the next figure 9.39b, okay, they are also similar except that the clock signal to the PMOS that is with NMOS logic block is an inverted clock signal. We call it as a this section. Okay, I don't know how to mention. Okay, this is actually called fine, but this is with a bar. It's actually with an inverted clock signal. Okay, this is we call it as this name. Okay, for figure 9.39b. Okay, this is figure 9.39b. Okay, the difference is only this. Okay, the clock signal that is input to the PMOS. Okay, the difference is this one. Okay, and then the sections also we call it differently. Okay, so for figure 9.39b, it is when all logic stage perform pre-charge, discharge operations when the clock signal is 1 and all stages evaluate output level when the clock is low. Okay, so when the clock signals change to the input of different logic blocks, then the pre-charge and the discharge process and also the evaluations phase will also be different. Okay. So a pipeline system can be constructed by simply cascading, alternating the fine and the fine bar sections. Okay, inverted fine. Okay, but it means the inverted clock signal sections. Okay, the pipeline system we can refer to the figure 9.39c. Okay, which is this one. Okay, this is the pipeline system. Okay, and each of the sections here is actually refers to these two diagram. Okay, in this part C, instead it is represented as a block, that label with the section. Okay, as in all dynamic CMOS structure, NORA CMOS logic gate also suffer from charge sharing and linkage. To overcome the dynamic charge sharing and soft nodes linkage problem in NORA CMOS, another circuit technique is to use known as zipper CMOS. Okay, this zipper CMOS will not be covered in this topic. Okay, so this slide stated some of the issue that is rise in NORA CMOS logic. Okay, so the issue is the charge sharing and linkage. Okay, and this problem can actually solve, okay, with another circuit technique, which is a zipper CMOS. Okay, so this will be the end of the topic. Okay, there is a summary here. Okay, in dynamic gates, the clock signal is needed. Okay, there are two modes, which is the pre-charge and evaluation phase. Okay, and also no static power dissipations. Okay, since this is a dynamic circuit, so the power dissipations involved will be in another types of power dissipations, but not static power dissipations. Okay, and then for domino logic is attractive for high-speed circuit. Okay, the speed is 1.5 or double faster than the static CMOS. And also there are many challenges in domino logic. Okay, the challenges are due to the monotonicity, linkage, charge sharing, noise. Okay, so all this I didn't discuss in details with you, okay, because I have no time to cover all together, and also I consider whether you can absorb all the informations and knowledge that I cover if I cover, okay, if I cover all this, okay, because there are more important topics that I will have to cover later. Okay, some of the challenges here will also be covered, so not all. Okay, so in domino logic is widely used in high performance microprocessor. Okay, so this is a summary for this topic. Okay, so I see I don't have much time. Okay, so I will quickly to brief you about the assignment. Okay, for lecture class, I will end the class a bit late today. Okay, since I need to brief you on assignment, so I will take more time to brief you on this one. Okay, lab-based assignment. Okay, this is assignment that I have uploaded to you in Google Classroom. I'm not sure whether you notice about it or not. Okay, the assignment is about design and simulations of combinational logic gates. Okay, and then the coursework mark consists of 50%. So means that this assignment, you will have to write a report, and then the report is also important. All must submit. Okay, and then the deadline of submissions is in week 11. Okay, so what is the date of week 11? Okay, so now I want to inform you the submissions deadline for the assignment report will be on Thursday. Okay, Thursday 31st March, mean by end of this month. Okay, in week 11. Okay, I understand that most of you will need to submit your draft thesis by week 10. Okay, I hope I didn't remember wrongly. Okay, I remember it is by week 10. All of you have to submit thesis. So I hope that after you submit thesis, you will be able to submit all your report, okay, in week 11. Okay, week 11 on Thursday by end of this month, 31st March. Okay, so please take note. Okay, so I will, okay, if necessary, I think I will put this deadline again in Google Classroom to remind all of you. Okay, and for this assignment, okay, it is an individual assignment. Okay, I make it individual because I see that the assignment given is not difficult. Okay, and then if you really done the lab report yourself, means that you will be able to finish this assignment yourself as well. Okay, so I make it an individual assignment. Okay, you also can discuss with other course mate, but make sure that the content and then the discussions of your result must be different. Okay, if any content or discussions that I found similar, I will deduct your mark. Okay, in the report, okay, what to include? Okay, title, objective, introductions, design methodology, results, discussions, and conclusions. These are all the content, okay, that has to be included in the report. Okay, the format here is also stated, and then all report also must be submitted in soft copy, okay, to Google Classroom. This is as usual. Okay, I will assign the submission later. Then you can submit your lab. You can submit the report. Okay, and then the marking rubrics of this assignment is also as attached. Okay, you can refer to the marking rubrics to see how your assignment report are assessed. Okay, and here this is the assignment given, the task. Okay, there are two tasks here. Okay, task 1 and task 2. Okay, task 1, the Boolean function is given. Okay, there are two Boolean functions given. You have to choose any one. Okay, choose one function to design in the schematic transistor level diagram and the physical layout of the combinational logic gates using electric VLSI design software. The layout design must be applied with appropriate optimization techniques to obtain the optimized polysilicon order for the selected Boolean function. The layout dimensions must be limited to 80 micrometer by 85 micrometer. Okay, means that the layout dimension, you must make sure they are within these dimensions given. Okay. Okay, later I will show you a samples of report, what you can actually include. Okay. Okay, so for task 1 is not difficult. Okay, you will have to use the electric software, okay, to design all the diagram, okay, based on the Boolean functions that you choose, and then you need to simulate to get the output. Okay, and then the output, you can actually verify using the theoretical one. Okay, the output waveform. Okay, how to verify? Okay, okay, I have a sample report. I will show you. Okay, then you know what you can include in this report. Okay, all these can actually help you to gain the mark. Okay, and then the result, okay, the simulated result, or how you can compare it with the theory one. Okay, so this one is the report. Okay, you can take as reference. Okay, so this is a report from your senior. Okay, with title. Okay, title must not be in this form. Okay, you can just define a title, design. Okay, not define, sorry. I already give the title to you actually. I just remember. Okay, so this is the title. You can just include this title. Okay, you no need to define yourself. Okay, objective also. Okay, objective you can define yourself if not defined for you. Okay, theory. Okay, theory, this is about the background. Okay, background of your study. Okay, for the assignment. Okay, this one you don't need to include many informations, just the important one that is related to your work. Okay, and the most important part are the methodology. Okay, methodology is about the design methodology. Okay, this is the content. Okay, schematic diagram. Okay, schematic diagram, there is a pull up and pull down network. Okay, you also can include. Okay, and with the Boolean function. Okay, Boolean, there is a Boolean function for both. Okay, we can define. You also can put this one. Okay, and then this is the truth table. Okay, just now I mentioned to you, we can also verify the stimulated output theoretically. Okay, we use these two tables to verify it theoretically. Okay. Okay, since the Boolean functions we already know, then we can draw a truth table, okay, to know what is the expected output. And then from this truth table, with the expected output, we can compare with our stimulated output result. Okay, after the schematic diagram, then the layout, okay, layout design also is one part of the design methodology. That one you also have to include. Okay, so to draw this layout design, if you apply the ULI path and stick diagram, then you will have to put, okay, under this design methodology. So all this you see, you can include. Okay, and then the physical layout all must follow the design rules. Okay, so some of the design rules you also can include. Okay, this is the layout and this is the 3D view of layout. Okay, so that is the idea, okay, to put for design methodology. Okay, there is the content. Okay, all this you learn before, so it's not difficult if you want to do the first task. Okay, the first task should be okay, okay, for all of you. Okay, and then the result and discussion. Okay, the result and discussions here you can discuss on the result. Okay, not only on the result, you also can discuss on the spice code. Okay, when you stimulate your diagram, okay, you will need to stimulate the spice code. You can discuss the spice code. Okay, and also you can discuss on the rules checking. Okay, so you see here, this is to show that the DRC, ERC, and NCC all pass. Okay, so this is the evidence of the uh, validity of your of your design. Okay, without any error. Okay, with all the rules checking pass. Okay, this is spice code, and this is the result. Okay, so the result again can be discussed together with the truth table and also with this can note. Okay, can map. Okay, sorry, can map. Okay, and this is the conclusion. So all this content you can include. Okay, and have to include. Okay, or will give you marks. Okay. Okay, and then marking rubrics. Okay, this is the marking rubrics. Another marking rubrics for assignment. Okay, it's not the same with the ones that I give you for the lab report. Okay, the assessment is quite similar. The mark allocation is quite similar, except that this one, there are still some difference here. Okay, you can take a look, and this one you have to include in the report. Okay, when I mark, I will directly refers to the marking rubrics, and then I will give mark. Okay, so these marking rubrics and then the cover page you have to include in the report. Okay, so I think that is for task 1. Okay, task 2. Okay, task 2 I think is also not difficult. Okay, for some of you. Okay, this task 2 is based on the design in task 1. Okay, resize the width of PMOS to increase it by appropriate factors to make it larger than the NMOS. For example, the width of PMOS can increase to 10 if the width of the NMOS transistor is 5. The length of both transistors should be constant. Compare using two different width values of PMOS to observe any effect on the output. Okay, and etc. Okay, all this you read yourself carefully what you need to be done in task 2. Okay, it is actually about the size of the NMOS and PMOS you need to vary. Okay, and also some of the parameters like the load capacitance. Okay, you also need to vary to see what is the effect to the output of the circuit. Okay, so all these you must address it in your report. Okay, I think that is all my briefing for assignment. Okay, any questions? Okay, if no questions, then we can dismiss class now. Okay, all of the attendance form I have received. Okay, There will be a tutorial class later, so some of you have to stay back. Okay, so we can dismiss now. Thank you.